So let's look now at how the graphs of f and f inverse are related. We know that the equation y equals f inverse of x is exactly the same equation x equals f of y, except it's rearranged just a little bit. If we want to graph the equation x equals f of y, which is the graph of the function y equals f inverse of x, we note that this equation results from switching the roles of x and y in the equation y equals f of x. So the graph of the equation y equals f of x is the graph of the function f of x, and the graph of the equation y equals f inverse of x is going to be the graph of the function f inverse. And this transformation of the equation y equals f of x to x equals f of y results in a transformation of the graph amounting to reflection in the line y equals x. The graph of y equals f inverse of x is the graph of x equals f of y, which turns out to be the reflection of the graph y equals f of x in the line y equals x. Because to get from here y equals f of x to here y equals f inverse of x, we're just switching x and y in the equation. Recall that the reflection of the point x1, y1 in the line y equals x just switches the x and the y values. So the reflection of that is y1, x1. And so therefore, the point x1, y1 is on the graph of y equals f inverse of x. If that is true, then we must have y1, x1 is on the graph of y equals f of x. So that's the same as saying that y1 equals f1, x1 if and only if x1 equals f of y1. So it's the same as our algebraic equivalence from before. Let's look at the graph of f and f inverse for a function that we've worked with. If we take f of x equals 2x plus 1 over x minus 3, then the graph of y equals f of x is shown in blue here. And we see the point 10, 3 is on the graph because 3 is f of 10. If you plug in x equals 10 here, you should get out 3 as f of 10. Now, the graph of f inverse is shown in purple here, and this is the reflection of the graph of y equals f of x in this line y equals x, which is the diagonal of the plane. And we see that the point 10, 3, when we reflect it in the line y equals x, it becomes 3, 10. And the point 10, 3 is on the graph of y equals f of x, and the point 3, 10 is on the graph of y equals f inverse of x. Now you can have some fun with this. We've put up two functions here that we've also played with a little bit. Y equals x cubed plus 1 and y equals the square root of 4x plus 4. And you should try to sketch the graphs of the inverse functions for these two one-to-one functions by taking their mirror image in the line y equals x. And try to do that before you look at the solutions on the next slide. So here I've graphed the inverse functions. Basically the graph is just the mirror image in the line y equals x, and the graphs of the inverse functions are shown in yellow here. And I haven't solved for a formula for the inverse functions here. I can draw the graphs without doing that. Here's another interesting and new function that we've looked at. We took this restricted cosine function, which we knew was a one-to-one function because it passed the vertical line test. So therefore it must have an inverse function. That inverse function is called arc cosine of x, or sometimes called cosine inverse of x. Also, we'd like to get a picture of what that function looks like by graphing its inverse. And this is something you can try to do before you see the solution. To get a picture of y equals arc cosine of x, you need to take the reflection of this function y equals f of x here and reflect it in the diagonal of the plane y equals x. This is what it looks like. The arc cosine function is shown in yellow here, and it's the inverse of the restricted cosine function. Note the domains get switched here. The domain of arc cosine is everything between -1 and 1, which is the range of the restricted cosine, and the range of the arc cosine is a bunch of angles between 0 and pi.